So in this question where they have this certain domain from 0 to 5 pi over 2, you're going to also make sure that you include the endpoints. So for example, what happens when you plug in 0 into this equation? What's it equal to? 1. Cos of 0 is 1. E to the power of 0, anything to the power of 0 is 1, so we just get 1 times 1. So we'd have 0, 1. What's going to happen when you plug in 5 pi over 2? Who right now is trying to do e to the power of 5 pi over 2 in their head? Anybody? E to the negative 5 pi over 2? Why don't we do cos of 5 pi over 2 first? And then see what happens after we do that. What's cos of 5 pi over 2? 0. So that makes it a little bit easier instead of trying to calculate e to the negative 5 pi over 2 in your head first. So we're going to have those endpoints on our graph as well because we're only looking at the domain from 0 to 5 pi over 2. Also, when we're finding our x-intercepts, that's going to go back to your trig stuff and figure out your powers. First of all, should we just do this one together? Okay. All the preliminary stuff, by the time we're done it, we'd almost be done the question. A couple of things. If we want to find the exact values of our x-intercepts, that's when our function is equal to 0. So we have this. It's two things multiplied by each other, so in a sense, we can look at where is e to the negative x equal to 0 and where is cos of x equal to 0. And again, we're only looking on the domain from 0 to 5 pi over 2. Which of those two seems an easier task to start with? Let's do the easier one first. The cos or the e to the negative x? The cos? Okay, so thinking about your unit circle and thinking about where cos is equal to 0, what values would you have? Pi over 2, 3 pi over 2, and we would include 5 pi over 2 as well, but we already figured that one out. So those are our x-intercepts. Now we go to the harder task. Where is e to the negative x equal to 0? Never. This is why guessing and checking is a very bad option in this one. Because if you guessed and checked, you'd never find something. Now, why is it never? What was the reasoning you came up with, or how did you reason that you came up with never? Okay, anything with an exponent, any exponential function looks like this, right? Doesn't matter what the base is. And there's always an asymptote here. It never equals 0. If you tried to make it equal to 0, you'd run into some problems. Okay? And even with the negative there, if we think of our transformations, what does that negative do? It's going to flip it, right? Does it flip it over the y, or does it flip it over the x-axis? Okay, flips it over the y-axis. So this original graph here, this part would get flipped over and look something like that. Okay? So even with the flip, we can still see that it's never equal to 0. So it'll often be the case that you get an e to the x that you can factor out in front, and that won't affect finding any of your x-intercepts. So there we found our x-intercepts. That's going to help us with our original graph. We're going to find the coordinates of the first two stationary points, and then we're going to sketch the graph. So in order to find our stationary points, we're going to have to do our derivative. Keep one the same. Let's keep cos x the same. What's the derivative of e to the negative x? e to the negative x, and then multiply that by a negative 1 for the chain rule. Plus, keep the other one the same, multiply by the derivative of cos. The derivative of cos is negative sine x. Again, as I said before, it's often with these ones with e to the negative x, you can see you could factor that out again. Okay? You can in fact factor out a negative e to the negative x, leaving you with cos x plus sine x. So if we wanted to find our stationary points here, well, if we make it equal to 0, again, this is never equal to 0. But what do we do here? We're basically looking where cos is equal to negative sine x. Any strategies for solving this? Unit circle. So how would you, what would you be looking for on your unit circle here? Okay. Pi over 4 family, they're the same, but one of them has to be. So what quadrants does that happen in? Quadrant 2 and quadrant 4. So that's one way to look at this. You're thinking of your unit circle. Cos and sine have to be the same, but one has to be positive, one has to be negative. So you get quadrant 2 and quadrant 4. If we're doing that, we get 3 pi over 4 and 7 pi over 4. In the range that we were actually doing, it asked us to find just the first 2 stationary points, so that would be enough. Up to 5 pi over 2, would we have any more of those? 5 pi over 2 just goes to quadrant 1 again. So those would be the only 2 in the domain that we're asked to find. Okay? Now, I like this, going like this. Another thing you could do in this situation that can be very helpful is take this equation right here, divide both sides by cos. Okay? It rules out that cos could never be 0. So we have to sometimes be careful in equations when we're dividing by a trig function. So before I do that, I just check. If cos is 0, is sine 0 ever at the same time? No. So I know that I will be okay in doing this in this situation. But dividing both sides by cos gives me negative sine x over cos x. I'm going to put the negative on this side just because I can. And what's sine x over cos x? Tan. And you get these same results, probably even easier, because now you're thinking, where on my unit circle is tan equal to 1? That's part of my pi over 4 family. It's negative, so quadrant 2 and quadrant 4 come into play again. And you would get the same answer of 3 pi over 4 and 7 pi over 4. So sometimes when you get this situation, and it does happen a fair bit, where cos and sine are equal to each other, you can change it to tan and then figure it out that way. Or you can just use the logic that we did before and think of your unit circle of where they're the same. Okay, so now we've got our 2 values where it's equal to 0. I'm going to put 0 on here because that was an endpoint, and 5 pi over 2 because that was an endpoint for what we were looking for. I'll put 3 pi over 4 on here and 7 pi over 4. I'm not worried about the spacing, that spacing makes sense. And now we're going to try values in there to find out where a function is increasing and where a function is decreasing. So between 0 and 3 pi over 4, what would be a number in there? Pi over 4. So if we tried pi over 4 into our derivative, because that's where we're going to find out if it's positive or negative. First of all, this is always never equal to 0. This first part, always negative. That's the first thing we need to look at. If you plug in pi over 4, which is in quadrant 1. Both cos and sine are positive in quadrant 1. And if you're adding two positive numbers, you should still get a positive number. If this is always negative and this will be positive, we know that this section is negative and we're going down. Between 3 pi over 4 and 7 pi over 4. Nice number seems like pi. That seems to be one that we could easily calculate. Okay? Cos of pi is negative 1. Sine of pi is 0. Negative 1 plus 0 will be negative inside the brackets. Negative times a negative. This section will be positive and will be going up. And finally, between 7 pi over 4 and 5 pi over 2, I'd probably pick 2 pi. Again, cos is 0, sine is positive 1. No, cos is 1, sine is 0. Negative times a positive negative, it'll be going down again. So in the range that we were asked for, we now know how it's going up and down. Okay. If the range had been extended, there would be way more values that you'd have to solve for, because you'd have to figure out all the places where tan is equal to negative 1, and there'd be an infinite amount of them. So it would be continuing this pattern up and down as we go. Now, as far as putting these points and where they would be, first of all, we know that 3 pi over 4, 1, that's a local min. And this one here is going to be a local max. And this for sure is where we're going to need our calculator. Because cos of 3 pi over 4, we could do that without our calculator. We know it's negative root 2 over 2. But e to the negative 3 pi over 4, no. So if someone would calculate the first one and somebody else calculates the second one, then we'll have those values. All right, what did we get? Anybody do the 3 pi over 4, 1? Minus 0.06. 6, 7 or 7? 6, 7. Woo! Fancy. And the other one? .0029. So some pretty tiny numbers. The limit of this one as x goes to infinity, since this e to the negative x graph, as x gets bigger and bigger, gets closer and closer to 0. This one will, as you go to infinity, will go to 0 as well. So it makes sense that as we're going further along to the right, that our values are getting smaller, because it will be getting closer and closer to 0. Okay, so it didn't ask us for inflection points. We could find them, but that derivative, you want to do the inflection points? People are shaking their head, because we'd have to do another product rule there. We could do it. I think we're going to get a pretty good sense from the graph of what we have already. So we're going to graph it from 0 to 5 pi over 2. I'll just mark 5 pi over 2 over here. We know that it's decreasing and it's going to start, our starting point is at 0, 1, and at 5 pi over 2 it's back here at 0. So 5 pi over 2, we're back here at 0. I'm going to put 1 up there, and we know that at 0, we're at 0, 1. Putting our other zeros on here, we know that we had zeros at pi over 2 and 3 pi over 2. So those will be other x-intercepts. At 3 pi over 4, comma, negative 0.67. So 3 pi over 4. So this would be pi over 2. Pi would be here. 3 pi over 4 would be about here. And we're at negative 0.67. That's our local minimum. And then at, so this would be 2 pi at 7 pi over 4, which would be right here. Negative 0.067. Oh, I see what you're saying here. Oh, there we go. So there, negative 0.067. And then this one at 7 pi over 4, 0.0029, really close to the x-axis. And when we go to play a little bit of connect the dot, it's going to be decreasing, increasing. Oh, man. Whew, I went a little bit too crazy there. Start that over again. Decreasing. Hits a minimum here, and then look at it increase through this point. Hits this maximum. Now it decreases. Yes. If you tried to graph this on your graphing calculator from 0 to 5 pi over 2, it probably you would see just sort of a straight line. And unless you zoom in, we got one there. Here's the right window. We'll put it up on the, we'll take a picture of this. Right? You can hardly see anything there. Well, especially with the darkness of the screen. But if I turn the light on, then it's too bright. No, that's not bad. So you can't even see. You can see the little minimum here. If we would go to this part and actually zoom in on it, we could, if I go to your window here, and instead of going from y min at negative 1, and we just go to negative 0.0, how low did it go? 0.01, is that enough? To 0.02. We can see a little bit more of a difference in the graph. Comes down, goes through our x-intercept, hits the maximum, and then it starts going back down again.